My dear students, now we are going to look at design of 4-bit synchronous counter. In this counter, what we try to do is just we use 4 flip-flops because it's a 4-bit. So as usual, we will be looking at the various steps. So the step 1 says that try to find the number of flip-flops required. Directly it is known. Actually 4-bit synchronous up counter is nothing but modulo, okay, how much it is? 16, modulo 16 operation. So n is equals to 16. Capital N is equals to 16. 2 power n should be greater than or equals to n. So 2 power n greater than or equals to 16. For n is equals to 4, 2 power 4 should be greater than or equal to 16. So this is nothing but 4 flip-flops required to design this 4-bit synchronous up counter. What type of flip-flop that you would like to use? So let's use T flip. Okay, draw the state diagram. How exactly it will be moving from? So from 0 0 0 0, next it will go to 0 0 0 1, next it will go to 0 0 1 0. Likewise it will go up to 1 1 1. So if present state is this, next state is this. If present state is this, next state is this. Okay. Likewise, it will be moving from one state to the other state. So just we will look at the excitation table, how it has to be excited. That means what input should be given. The excitation table is something like this. From 0 0 0 current state means in the memory it is 0 0 0. Now this memory has to be updated to 0 0 0 1. How it will get updated? If you give an appropriate input, it will get updated. So that is what exactly we are trying to find it out. Okay. Then uh, we will look at excitation table. But exactly before going to excitation table, as we know how exactly state diagram it should be, so we will draw the state diagram. Only thing is, we should have a large dia for this diagram. So what exactly that I am trying to do is, okay, so we are going to have, okay, how many states? 16 states, right? So it should be like this. So once, then 8 more states. Just let me has this, then take the next one. Okay. So what is the present state? Is 4 zeros. What is the next state? 0 0 0 1. What is the next state? Okay. So let me have little big this one so that I can write it. So 0 0 1 0. Then 0 0 1 1. Then 0 1 0 0. Okay. Then 0 1 0 1. Then likewise this is 5. Next 0 1 1 0. 0 1 1 1. 1 0 0. 1 0 0 1. Okay. So next 10. 1 0 1 0. 1 0 1 1. Okay. 1 1 0 0. 1 1 0 1. 1 1 1 0. 1 1 1 1. So from here to here, from this state to this state, 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 this to this state to this state, from this state to this next state. Okay. So next I can have this, then going to this state, next state, next state, next state, next state, then next state. So this is 4-bit synchronous up counter state diagram. Okay. Once the state diagram is done, then what we look is excitation table. What is excitation table? Just we have seen excitation table. What inputs to be given, what is exactly it is to be get excited. So that it will go from state, present state to the next state. So four flip-flops required. Present state is QA, QB, QC, QD. Let's say. Then QA plus 1, QB plus 1, QC plus 1, and QD plus 1. Okay. So when 0, 0, 0, next is 0, 0, 1. When 0, 0, it is 0, 0, 1. When 0, 0, 1, it is 0, 1, 0. So likewise, okay, it will go from 4 zeros to 4 ones for all the cases. So now we try to look at the QA and QA plus 1. 0, 1, 1, 0. So it continues like a 3-bit up counter. Okay, always it is changes. So what I try to do is TA is 1 for all cases. You can observe that. Okay, from the observation, TA is always. Now let's look at the TB, TC, and TD. If you look at QB and QB plus 1, these two are zeros. This is 0, 1. Okay, for 0, 0 it is 0. For 0 and 1 it is 1. Right? As we know, Qn plus 1 T. 0, 0 is 0. 0, 1 is 1. 1, 0 is 1. 1, 1 is 0. Excitation table for a T flip flop. So from that, if at all I look at and I try to write it, so 1, 1 is 0, then 1, 0 is 1. Okay. So further 0, 0 is 0, 0, and then this is 0 and this is 0. So it is 0, this is 0, and this is 1. So it is 1. So what exactly that is observed is it is 0, 1, 0, 1, 0, 1. It is true for rest of the cases. 0, 1, 0, 1, 0, 1, 0, 1, 0. Now next let's look at the QC and QC plus 1. So first, if you look at first three zeros, here also first three zeros. So 0, 0, 0. Now this is 0, whereas this is 1. So it is 1. Similarly, if I look at here it is 3 ones, here it is 3 ones. At that time I can make 3 zeros. This is 1, whereas this is 0. So we have certain pattern, 3 zeros followed by 1, 3 zeros followed by. Rest of the case also it is same. So 0, 0, 0, 1, then 0, 0, 0, 1. Okay. Next what we try to do is try to compare here. This is QD and QD plus 1. Let's change the color, which will look different. QD here and QD plus 1. If at all you look at, except this case, all are same. So for this it is 1, for rest of the cases it is 0. Okay. So I do the same. I try to enter those values. So this is 1, this is 0, 0, 0, 0, 0, 0, 0. Next, if you look at what exactly happening is the same thing. That is next 7 ones and here 7 ones. Okay, this is 1, this is 0. So what I get here is just I will get here as 1 and rest of the cases it is 0 because it is always okay. From this what I do? From this what I do is I will get the expressions for TA, TB, TC. Okay. So why we are getting like that? TA. So what we are trying to do is to get the TA values and TB values and TC, TD. Okay. TA, TB, TC, and TD. These are the input. What are the inputs to it? Inputs are QA, QB, QC, and QD. Okay. So we are trying to get some certain combination circuit. Okay, from QA, QB, QC, QD. Expressions for TA, TB, TC, TD. So that by applying those gates, okay, by processing the present state, I'm going to give certain input to the flip-flop so that I'll go to the proper next state. Okay. So what I can say is TA is function of QD, QC, right, comma, QB and QA. It is valid for rest of the cases, TC and TD. Okay, that is the reason why we are processing that. So here it is QA, QB, QD and QC. So what I need to do is I enter the values all ones, all ones. Okay, this is the sequence that we know. So when I combine them, TA is equals to 1 forever. Next, what we try to do is we got 0 1 0 1 0 1. See here 0 1 0 1 0 1. So 0 1 0 1 0 1 is what exactly? You can write sigma m value. If you look at it, it is 1 0 1. After 1, it is 3. After 3, it is 5. So 1 3 5 7 like that I can write. So TB is sigma m. It is 1 3 5 7 9 11 13 and 15. So we know this is 1, this is 3, this is 5, this is 7, this is 9, this is 11, this is 13, this is okay. So this is QA and QB, QD and QC, right? So what exactly that we are going to get expression is simply by combining these 8 ones. What I will get is expression for this as expression for TB is in this QC QD gone. In this what is there is QA. So we got okay. Next what we try to do is we'll go for expression for TC. TC is sigma m. What exactly it is? It is 1 for from the table. You can see here. It is 1 for here it is 1. 0, 1, 2, 3. For 3 it is 1. Okay. Then for 3 it is 1. 4, 5, 6, 4, 5, 6, 7. So 3 is 7. Okay. Then it is 1 for what exactly? 11. So 3, 7, 11 and 15. 3, 7, 3, 7, 3, 7, 11 and 15. So 3, 3 is here, 7 is here, 11 is here, 15 is here. So this is what exactly the combination. This is expression for TC. TC turns out to be okay QA QB. Okay. Next we need to look at TD. TD is equal to 1 for what exactly? There are only two entries ones in the table. The one which is 1 for 7, 1 for okay 15. So 7 and 15. So if you consider the 7 and 15 cases, 7 and 15, where is 7? 7 is here. Where is 15 is here. So if I take that and if I combine them, this is your QA, QB, QD and QC. Okay. So QD is your MSB, QA is your LSB. Okay. So in these two, here it is expression for TD. TD, what is TD? TD is sigma m 7 comma 50. For this the expression that I am going to get is TD is nothing but what exactly is in this two it is QC, here it is QB QA, so it is QC QB QA. Okay, this is the expression. So this is 1, TB is QA, this is QB QA, okay, this is QB, okay, QC QA, okay. If you go for 5-bit synchronous up counter, how exact it will be? This is for 4-bit. For 3-bit, how much we got it? What exactly we got it? For 3-bit, TA is 1, TB is QA, TC is QB QA. Similarly, if you go for 5-bit, TA will be 1, TB will be QA, okay, TC will be QB QA, TD will be, what is exactly, QC QB QA, TE will be QD QC QB QA. This is what exactly you are going to get extra. If it is a 5-bit synchronous subcounter, for 3-bit we got this, for 4-bit we got this, for 5-bit we are going to expect the same from these solutions. Okay. So rest is drawing the circuit diagram. Drawing circuit diagram is very simple. 4 flip flops. Okay. So I will take one flip flop here, another flip flop here, then another flip flop here, then another flip flop here. So what I try to do is I try to make the connections. So flip flop A, flip flop B, flip flop C, and flip flop D. So for these flip flops, what we need to do is we need to get their outputs and apply proper input. This is one which is TA. Okay, what is TB? Is QA. So whatever is there, this QA, I'll connect it to. I'll take this QA and QB. So here it is QB, here it is QB bar, it is QA, it is QA bar. So I'll take QB and I'll extend this from here. I'll take this QB, this I'll give it an AND gate, that I'll give it to the next. This is TC. Okay. So here it is QC. Okay. So here it is QC bar. Here it is QD bar. And here it is QD. And here it is TD. So what I try to do is whatever is there, QA QB, I have QA QB. I'll take QC and this I'll give it to the AND gate, which is QA QB QC, that I will give it to TD. Okay. For all of them there is a common clock. The common clock is like this. So this is what exactly the 4-bit synchronous up counter. Similarly, we can look at 4-bit synchronous down counter in the next class.